Welcome to the first lecture on properties of triangles. So, in the subsequent lecture and also in this lecture, we will be primarily interested in finding the relations between the sides and angles of a triangle. So, today we will be mostly discussing some of the very basic and fundamental relations. So, the very first fundamental relation which comes to mind is known as the sine law, and what it states is that suppose let us say that we have a triangle ABC So, let us say that this is triangle ABC whose corner points or vertices are A, B and C, and we shall also be denoting the angles. So, the angle at the vertex A will be denoted by uppercase A, the angle at vertex B will also be denoted by an uppercase B letter, and similarly the angle at vertex C will be denoted by uppercase C. The length of the three sides, so of course the three sides are AB, BC and AC. So, the convention that we will be following in all subsequent lectures is that we will be denoting the length of the side BC, which is opposite to this angle A, by a lowercase letter a. The length of this side, which is opposite to the side or this side which is opposite to the vertex B, or we can also say that this side is opposite to the vertex to the angle B. So, this particular side which is opposite to angle B will be denoted by the length of this side will be denoted by a lowercase letter b, and this side is opposite to angle C, and therefore, the length of this side will be denoted by lowercase c. So, this is the convention that we will be following throughout our discussion in subsequent lectures and this lecture also. So, now let us come back to the very first property of or the relation between the three angles and the three sides. So, essentially if you see, we have three angles, angle A, B and C, and we have three sides A, B and C. So, let us drop a perpendicular from this vertex A onto the opposite side BC. So, let us say that this perpendicular meets this side BC at a point D. So, this is 90 degrees, and then we can write that if you look at this particular, so if you look at this particular right angle triangle here, so this is 90 degree and this is the hypotenuse. So, we see that this length AD, from the basic definition of the trigonometric ratios that which we have already seen in the first lecture on trigonometric functions, we know that this side AD is nothing but equal to C times sine of the angle B. So, and then if we look at this other right angle triangle, so now we are going to look at the right angle triangle ADC. So, in this right angle triangle, so AD is common to both these right angle triangles. So, but if we focus on the right angle triangle ADC, what we see is that AD equals B times sine of C, because here for this triangle B is the hypotenuse, whereas for this triangle C was the hypotenuse. Now, since AD and AD are equal, so by comparing these two equations, what we end up getting is that C sin B equals B sin C, or in other words, C by sine of angle C is equal to B by sine of angle B. And in a similar manner, in a similar manner, if we drop a perpendicular from this side C, from the, if we drop in a similar manner, if we drop a perpendicular from the vertex C onto the side AB. So, let us say if this is the perpendicular here, then by repeating similar arguments, so then we have to take this right angle triangle, and then we have to take the other right angle triangle, which is this. And then if we repeat similar arguments from this particular triangle here, so this is a right angle triangle where this is the height and let us say this is the hypotenuse. So, and let us say that this point here is E. So, what we get is that CE equals, so CE equals B sine of A, but then this is also a right angle triangle, this is also a right angle triangle. So, I am referring to the right angle triangle CEB now. Now, in this right angle triangle we can again write that CE equals A. So, this length A into sine of B. So, these things obviously follow from the definition of the sine of an angle in a right angle triangle. So, for example, if we take if we just redraw, so I have essentially redrawn this particular right angle triangle CEB here. So, this is our angle B. So, we know from the trigonometric definition of the trigonometric ratios, we know that the sine of angle B is equal to the side CE, which is CE over the hypotenuse, which is BC, and this is equal to CE over, but BC is equal to A. So, this is A. So, we have sine B is equal to CE over A, and from this equation it follows that CE is equal to A sine B. And therefore, since CE is the same here, this B sine A and A sine B are also equal. And from these two set of equations, what will follow is that, so from these two set of equations it will follow that B divided by sine B is equal to A divided by sine A. So, from here we will get B divided by sine B is equal to A divided by sine of A. But when we compare this and this, eventually we see that all these three, so C over sine C, B over sine B and A over sine A are all equal. So, then we can finally write that A over sine A is equal to C over sine C is equal to B over sine B, and this is what is precisely known as the sine law. And it just does not hold in this case. The first triangle that we had drawn was an acute angle triangle. So, this triangle ABC that we had drawn, it appears to be an acute angle triangle, but please note that this result is true for any type of triangle, not just an acute triangle. So, this is also true for triangles where one of the angles is obtuse, for example, or even for right angle triangles this is correct. So, just like the sine law, there is the cosine law also, and we will again try to derive it here. So, let us take the same triangle again. So, we again have the triangle ABC, and then we have a perpendicular from the vertex A to the side BC, and it meets the perpendicular meets the side BC at the point D, and then this of course is C, and this side is B, the length of this side is B, the length of this side is A. If we now focus on the right angle triangle ABD, which is this right angle triangle, we can write down the Pythagoras theorem. From the Pythagoras theorem, we can write that AB whole square equals AD whole square plus BD whole square. So, AB whole square is AD whole square plus BD whole square. But what is BD? BD is exactly equal to BC, this whole length BC minus CD. So, we are going to, in this equation, we are going to substitute BC minus CD in place of BD here. So, what then we get is that AB square is equal to AD square plus BC minus CD whole square. And then a little algebra shows that this is equal to AD square plus BC square plus CD square minus 2 times BC times CD. And then we try to combine AD square with CD square, and if we see, then from this right angle triangle here, so if we just see this right angle triangle ACD, then in this right angle triangle, again from the Pythagoras theorem, we see that AD square plus CD square, so AD square plus CD square is actually equal to AC square. So, this plus this is actually AC square. So, then what we have here is AC square plus BC square minus 2 into BC into CD. But what is AB? So, AB is actually equal to C. So, the left hand side is C square equal to AC is equal to B. So, this becomes equal to B square plus BC is exactly equal to A. So, this term becomes A square minus 2 into A, because BC is A, times CD. So, CD here, so this angle is C. So, therefore, if I look at this right angle triangle here, then from the basic definition of the trigonometric ratios, I know that CD is equal to the hypotenuse, which is B, times the cosine of the angle C. So, I am going to use this here, and then what I get is 2 times BC, which is A, times CD, which is B cos C. So, I get B times cos of C. And therefore, from here, what we can further write is that cos of the angle C is equal to B square plus A square minus C square over 2AB. So, using this formula, the use of this formula, so this is called the cosine law for the angle C. So, it says that in this triangle ABC, if we know the length of the sides of the triangle, which is A, B and C, then by using this formula, we can exactly find out the cosine of the angle C. Now, we know that the angle C will always lie between 0 and 180 degrees. It has to lie between 0 and 180 degrees, and for that we know that because if you remember, the range of the cos inverse function is from 0 to 180 degrees or 0 to pi, and therefore if cos c is equal to this value, then it is implied that c is exactly equal to cos inverse of b square plus a square minus c square over 2ab. This is because we know that the angle c, which is an angle of one of the three angles of the triangle, and therefore it is sure that this c has to belong to 0 to pi. So, this we already know that it has to belong to 0 to pi, and since this set 0 to pi is actually the range set of the cos inverse function, since this is the range set of the cos inverse function, it therefore follows that from here this is true. C is exactly given by cos inverse of b square plus a square minus c square over 2ab. In a similar manner, we can also show that cos of a, cos of the angle A is, so there is a pattern actually, that if we have to find the cosine of the angle C, the denominator will be 2 times the product of the other two sides except the side of length C, and in the numerator we will have the sum of the squares of the two sides other than the side of length C minus the length of the side C, minus the square of the length of the side opposite to this angle C. And therefore, you from that pattern, and also by just following the same proof for angle A, what we get is cos of angle A is b square plus c square, because these two b and c are the sides, the other two sides apart from the side of length A, minus a square by 2 bc, and also that cosine of b is a square plus c square minus b square over 2ac. So, essentially the cosine law is basically helping us to find out the three angles if we are given the length of the three sides of a triangle. So, if we know the lengths of the three sides of the triangle, then using the cosine law we can also find the three angles. So, another set of useful formulas that will be of lot of help in the subsequent discussions and proofs is basically the expression for the sine and the cosine of the half angles. So, we are interested in deriving expressions for sine a by 2, cos a by 2, and likewise sine b by 2, cos b by 2, and sine c by 2, cos c by 2. So, we would like to derive expressions for these sines and cosine of half of the angles of the triangle in terms of the lengths of the sides of the triangle. So, that is what we will do next. From basic trigonometrical identities, we know that 1 minus cos A is equal to 2 sine square A by 2, or in other words, sine square A over 2 is 1 minus cos A the whole divided by 2. Now, since the angle A is basically one of the three angles of a triangle, it is guaranteed that the value of A will be between 0 and pi, and therefore, A by 2 belongs to the interval 0 to pi by 2. And from here it follows that sine of A by 2 is positive, And therefore, using this fact in this identity here, we can write that sin a by 2 is equal to the positive square root of 1 minus cos a over 2. And here we are going to use the cosine law formula for cos a in terms of the lengths of the sides of the triangle. So far we have sin a by 2 is equal to the positive square root of 1 minus cos a over 2, and from the cosine law we know that cosine of the angle A is b square plus c square minus a square over 2 bc. So, that is something that we just derived in the, so this is the equation that we are using now. So, we will replace this cosine of a here with this expression. So, when we do that, what we get is that sine of a over 2 is equal to square root of 1 minus b square plus c square minus a square over 2 bc over 2. So, all of this is inside the square root, and that is equal to square root of a square minus b minus c whole square over 4 bc. With a little bit of algebraic manipulation, it is easy to get this from here, and that can be written as, the numerator here can be written as a plus c minus b into a plus b minus c over 4 bc. So, then we have sine of a over 2 is equal to square root of, so we can write the, so both of these we can, so for example, for the first one here can be written as a plus b plus c, which is the perimeter, minus 2b. So, then we have a plus b plus c minus 2b into a plus b plus c minus 2c over 4 bc. And then let us define by S half of the perimeter of the triangle. So, a plus b plus c is the perimeter of the triangle, and this S is nothing but the semi perimeter of this triangle. So, that we will define as S. So, if you know the sides, the length of the sides of the triangle, then the semi perimeter is also known immediately. So, with this substitution here, what we get is that sine of a by 2 is equal to square root of 2 times, because this a plus b plus c is 2s. So, 2 times s minus b multiplied by 2 times. So, this will be 2 times s minus c over 4 bc, and the 4 and the 4 will get cancelled. So, this is simply equal to square root of s minus b into s minus c over bc. So, this is the formula for the half angle in terms of the lengths of the sides of the triangle. In a similar manner, we will try to find out an expression for the cosine of the half of the angle A. So, we are interested in finding out the expression for cos of a by 2. We know that 1 plus cos a is 2 cos square a over 2. We also know that since a belongs to the interval 0 to pi, it follows that a by 2 belongs to the interval 0 to pi over 2, and from here it follows that cos a by 2 is always positive, and therefore, from here we can say that cos a by 2 is equal to the positive square root of 1 plus cos a over 2. And here again we are going to use the cosine law. So, we are again going to use the cosine law, and we substitute. So, we from the cosine law we know that cos of a is equal to b square plus c square minus a square divided by 2b c. So, if we substitute this right hand side into this expression here, what we end up getting is that cos a by 2 is square root of 1 plus b square plus c square minus a square over 2bc, everything divided by 2, that is cos of a by 2 equals square root of b plus c whole square minus a square over 4bc, and that can be further simplified to b plus c plus a into b plus c minus a over 4bc, which is, so this thing is 2 times the semi perimeter S multiplied by, and this expression is b plus c plus a minus 2a. So, that is, so this becomes 2 into S minus a over 4bc. So, finally, what we get is that the cosine of the half angle of a is square root of S into S minus a over bc. And recollecting from the previous slide, we had got sin a by 2 to be equal to square root of S minus b into S minus c over bc. So, this is, if we recollect from the previous slide, so this is what we had shown there. So, I am just copying it here. And similar formulas for the half angles are also true for the angles B and C. Also, one can see that from here. So, first of all we observe that here we have a formula which, if we are given the values of the sides or the lengths of the sides of the triangle, then we can exactly find out the sine and cosine of the half angle of all the 3 angles. So, this is the formula for the cos and sine of the half angle for A, and similar formulas hold for the, so for the half angle of B, the formula is square root of S into S minus B over AC. So, even here there is a little bit of a pattern that for the half angle the expression is usually of this form. So, it is S times S minus, if the angle is A, then we have to put the side, the length of the side opposite to the angle A. So, that length is small a, divided by the product of the lengths of the other two sides. And for sine of a by 2, it is square root of S minus b times S minus c. So, note that b and c are the other two sides apart from the side of length a. So, b and c are the lengths of the other two sides divided by the product of b and c. So, following that pattern, we can easily write cos b by 2 to be equal to this, and then sin b by 2 is square root of S minus a into S minus c over AC, and likewise cos of c by 2 will be square root of s into s minus c over AB, and sine of c over 2 will be square root of s minus a into s minus b over AB. So, these half angles will be very useful later on. So, we now move on to deriving an expression for the area of a triangle, in terms of the lengths of the three sides. So, if we are given the lengths of the three sides, this particular formula, which is called as the hero's formula, will help us to compute the area of the triangle. So, let us say that here we have a triangle ABC, and so this side has length A, this is the side of length B, this side has length C, and as usual I again drop a perpendicular here at this point D. Then the area of this triangle is simply given by, so area is usually denoted with this Greek symbol delta. So, the Greek symbol delta is usually used to denote the area of this of triangle ABC. So, this is nothing but half into base into height. So, the base is BC. So, this is A. So, half into A. So, half into base multiplied by height. So, height is AD. So, area is A by 2 times AD. But if we look at this particular right angle triangle here, then we know that AD is simply equal to, so this length is C. So, AD is equal to C into sine of this angle, but this angle is B. So, AD is equal to C times sine of angle B. So, therefore, finally, what we have is the area is AC into sine B over 2. But then let us say we only want to, the hero's formula will eventually give an expression for the area only in terms of the lengths of the sides. So, this is an angle. So, we need to go further ahead, and so we will now make use of the half angles, that the expressions for the half angles, because we know that from again the trigonometric identity sine B is equal to 2 sine B by 2 into cos B by 2. So, we are going to use this trigonometric identity here, and then this area becomes equal to AC times sine B over 2 into cos B over 2, and for that, for these two we will use the cosine and sine of the half angle B that we had just derived in the previous slide. So, when we use these two expressions here, what we get is that the area of the triangle is equal to AC times, so sine B by 2 is square root of S minus A into S minus C over BC times, and cos of B by 2 is S into S minus B over, sorry, this will be AC, sorry, this will be AC, and this will also be AC here. So, this will then become equal to square root of S into S minus A into S minus B into S minus C. So, if we are given the values or the lengths of the sides of all the three sides of a triangle, then by using this formula we can find the area of the triangle. So, this formula is known as the Hero's formula. So, next we would like to discuss about the type of different types of circles which are associated or connected with a triangle. So, one of the circles which is connected to any triangle that you can think of is known as the circumcircle. Is known as the circumcircle. So, what is a circumcircle? Well, let us say that we have this triangle ABC whose sides are drawn with in blue color. Then if we just look at the vertices A, B and C, then we know that the vertices A, B and C, because it is a triangle, the vertices A, B and C are not collinear. So, the vertices A, B and C are not in a straight line, and therefore, we know that there has to be a unique circle which passes through these 3 points A, B and C. And that particular unique circle which passes through all these 3 points A, B and C is called the circumcircle. So, that is called the circumcircle, and it is clear that our triangle is going to lie in the interior region of the circumcircle. So, next, how do we draw this circumcircle? So, that is not very tough, because it is a circle, because the circumcircle is eventually a circle, it has to have a center. So, the center of the circumcircle is called the circumcenter, and we will denote it with the point O. But remember, the circumcenter, which is the point O, should be such that the distance of all these 3 vertices from this circumcenter has to be the same, and that is because the circumcircle is actually a circle, right. So, it should be true that OA is equal to OB is equal to OC. Now, but since OA is equal to OB, it follows that the circumcenter point O must lie on the perpendicular bisector of the line segment AB. This is because this circumcenter is equidistant. See, OA equal to OB basically implies that the point O is at equal distance from both point A and point B, and therefore, the point O has to lie somewhere on this perpendicular bisector of the line segment AB. So, this perpendicular bisector I have drawn with a red dotted line, as you can see here. Similarly, so we know that the center is somewhere here on the, it should be somewhere on the red dotted line. Similarly, since OB is equal to OC, so OB is equal to OC, because of that it must also be true that the circumcenter O must also lie on the perpendicular bisector of the line segment BC, because OB is equal to BC, which means that O is at equal distance from both B and C, and therefore, the point O must lie on this perpendicular bisector, which I have drawn with a black dotted line. So, the point O must therefore also lie on the perpendicular bisector of this line segment BC. And by a similar argument, because OA is also equal to OC, the point O must also lie on the perpendicular bisector of the line segment AC. Now, obviously, the first two perpendicular bisectors in red and black will definitely intersect at some point, which is here, and the third perpendicular bisector in blue has to also pass through it, So, this particular point here is the which is so this point here, which is the intersection of all the three perpendicular bisectors in red, black and blue. All of these three different perpendicular bisectors of the three sides are going to intersect at a common point O, which is going to be the radius, which is going to be the center of this circumcircle, and the radius of this circumcircle is called as circumradius. So, the radius of the circumcircle is known as circumradius. First objective now is to find an expression for the value of the circumradius of this circumcircle. So, for that we make a little construction over here. So, obviously, this length here is the circumradius, and one point which I forgot to mention is that it is not always true that the circumcenter should lie inside or in the interior of the triangle. It is very easy to construct examples where the circumcenter could actually lie outside the triangle. That is possible. So, here, so this is the radius, or the rather the circumradius. This is the circumradius denoted by capital R for the circumcircle. So, this is what is the circumradius, and we would like to find an expression for this circumradius. We know that this black dotted line is a perpendicular bisector of this line BC, and what that means is that this angle is 90 degrees, and the length of this particular length is half of this total length, which is a by 2. And then let us say that we connect we connect the circumcenter with the vertices B and C of the triangle, then from basic high school geometry, all of us know that, so this angle BOC, so we know that the angle BOC, which is basically this angle, so the angle BOC is actually twice of this angle, it is twice of the angle. So, for that we have to actually look at this circle in red. So, for this circle in red, we have, it is easy, and since this O is the center of this circle, it follows from basic high school geometry that angle BOC is twice of angle BAC. But angle BAC is nothing but angle A. So, this angle BOC is exactly equal to twice of angle A. So, this entire angle BOC is equal to 2 times angle A. And we further see that, so now let us focus on these two. So, this right angle triangle and this right angle triangle. So, for both of these triangles, what we see is that they have a common side, which is this, and then the length of this side is also a by 2 and this is also a by 2. That is because this black dotted line was a perpendicular bisector of BC. So, these two sides are equal, we have a side in common, and this of course is the radius of the circumcircle, and therefore, even these two sides are equal, and hence this shows that this right angle triangle is congruent to this right angle triangle. And from there, let us say that this particular point here is D. So, from here it follows that because these two triangles are congruent, it follows that angle BOD, so this angle BOD, so I am just talking of this particular angle here, angle BOD is basically half of this whole angle. That is because these two triangles are congruent, and hence angle BOD is simply equal to angle A. And then if we focus on this particular right angle triangle BOD. So, let us focus on the right angle triangle, this right angle triangle BOD. Then what we can see is that since this angle BOD is equal to A, it follows, and this is equal to R. So, we have seen that because of the congruency of this right angle triangle BOD and the right angle COD. So, this is point O and this is point D. So, because these two right angle triangles are congruent, we have already seen that angle BOD, which is this angle. So, angle BOD is equal to A. So, now if we consider this right angle triangle BOD, then it follows that sine of, so if we just focus on this triangle, and let me reproduce this triangle. So, we have this triangle. So, we are considering this right angle triangle BOD. The hypotenuse is basically the circumradius, which is this, and this length is A by 2, and we know that this particular angle is equal to A, and therefore, it follows that sine of A is equal to A by 2 upon R, and hence from here it follows that R is equal to A upon 2 sine A upon 2 sine A. And then for this what we can write is that R is equal to A upon, and then here again we can write this expression as we can use the half the sine and cosine expressions for the half angle A. So, then it is going to become 4 sine A by 2 into cos A by 2, because sine A is 2 times sine A by 2 into cos A by 2, and then we can use the formula for sine A by 2 and cos A by 2, which is, so we know that, so this is the formula for sine A by 2, and we know that cos A by 2 is square root of s into s minus A by BC. So, the product of sine A by 2 and cos A by 2 will be equal to A upon 4 into square root of s into s minus A into s minus B into s minus C, and then BC is going to go in the numerator. So, I have just substituted these two right hand side in this expression here. So, then but then by the Hero's formula we know that this is nothing but the area of the triangle, and therefore, the value of the circumradius is equal to the product of the length of the side divided by 4 times the area of the triangle. So, in the next class we will continue with some other circles which are associated with any triangle, for example, the incircle, and we will try to find expressions for the radius of incircle. Thank you.